Can I start? Yeah,
Yes.
hello. Yeah, thank you. Thank you very much for coming to the coffee meeting. And today I'm very happy to introduce the Singularity Theorem. And about 110 years ago, Albert Einstein proposed general relativity and the Einstein equation. And yeah, thanks to them, we can use them to calculate the orbital motion of the Earth around the Sun very precisely. Also, black hole can be predicted, and which was proved by gravitational wave detection. Also, the universe itself is expanding, and we can understand why and how the universe is expanding using the general relativity and Einstein equation. Okay, so in that sense, Einstein equation is frequently called as God's equation. However, 60 years ago, Roger Penrose proved that there is a limitation of general relativity. So, which is Singularity Theorem. So today I would like to introduce about that. Okay, so let me start. So singularity is defined like this. So space-time M4 dimension with metric can be null geodesically complete if three conditions are satisfied. So there is a non-compact Cauchy surface sigma 3 in space-time, and where the space-time is homeomorphic to sigma 3 times r. This is the time dimension. And the second condition is that there is a closed trapped surface J2 in M4. The third condition is strong energy condition, which is written like this for non-spatial vector. Okay, so yeah, I would like to explain what this means from now on. Okay, good. So Cauchy surface means something like this. So space-time is quite natural, so which has this three-dimensional space, and time is perpendicular to this, something like this. And this is no boundary, which has no boundary. This is an assumption, non-compact, so there is no boundary. So spatial, you can consider the kind of plane to, which is going to infinity, and the time vector can be defined something like this. Okay, good. So in that sense, future relative to sigma 3 and past relative to sigma 3 is clearly defined. And for each point in space-time, one line is corresponding. So global time-like vector can be defined, and which does not cross each other. So, and for any point in space-time, global time-like integral curve of global time-like field is corresponding. Okay, and space-time is filled with these lines. So from infinity in the past to infinity in the future. So in that sense, this is this curve complete. In that sense, complete means that is something like this, from infinity to infinity. So any time-like vector is going from infinity to infinity. This is the meaning of completeness. Okay, good. And so let's tell me about what is the future and what is the past. So let's go into the two-dimensional Minkowski space and space dimension and time dimension. And this is a future, time-like future, called as I plus j. So future of j, point j, and which is filled with null surface. Okay. So future is j plus its summation of I plus and E plus. I means time-like area surrounded by null surface. Then you can define future. Okay, good. So let me go to the second condition, J2. So what is closed trapped surface J? So yeah, let's consider the sphere, normal sphere S, and let's shoot. Let's emit photons toward outside and inside. And at some time later, what will happen? So photons toward the inside makes a sphere. Photons going outside makes another sphere. And let's compare that. Surface area. For normal situation, you agree like this. So original sphere, and for outside, so the surface area becomes bigger. For inside, smaller. This is quite normal. You agree? Everybody agrees with me. And you know black hole. For black hole case, what happens? So what is black hole? Okay. So even photons cannot escape from black hole. Okay. So for black hole case, within the event horizon, it's quite natural to consider that there is a closed trapped surface. So if you shoot photons toward the inside, which makes sphere, something like this. And for the black hole case, even if you will shoot photons outside, so it makes a sphere inside of the original sphere. This is the case for black hole. So for the black hole case, situation becomes something like this. So this is called as a trapped closed surface. Okay, so let's calculate the sphere area, something like this. And for the original area is written something like this. So this is the area component. On the blue sphere and red sphere can be expressed something like this. And let's calculate the expansion rate, how this area component change with a fine parameter like time. And this is the expansion rate. This is the differential of this quantity gives the expansion rate, how quickly the area expands or shrink. Okay? And the definition of closed trapped surface means that the initial condition of theta is negative. Okay, and there is a famous equation, Ray-Choudhury equation. This is quite a general equation, which gives you the expansion rate, time evolution of the expansion rate, which can be calculated, written something like this, and minus this one. So you don't have to remember everything. So in my case, in our case, this is 0. I don't explain the detail, but you can neglect this component. So the remaining thing is negative, negative, and negative due to the condition 3. So everything is negative. So expansion rate, time derivative of expansion rate is smaller than this. So you can solve this even by high school student, right? Then what happens is something like this. So theta evolves something like this to minus infinity with finite affine parameter, which means that the area. So if you shoot photons from sigma 3, the area becomes 0 within finite affine parameter. So it's close. Okay. So any gamma 1, gamma 2 are null geodesics from sigma 3, and which has an interaction, which is called as conjugate point. T. And it is well known that there is a theorem that any R behind the conjugation point can be connected by time-like geodesics. So this is a theorem. In that sense, this point is on the null geodesics. However, it is in the future horizon of time-like vector. So so R is belonging to I plus J. Okay, so which means that there is a future endpoint and this is a past point, so which makes a compact. This segment is compact. Okay, very compact. Then contradiction, proof by contradiction happens. So this is like a Zen question and answer, like a Zen Mondo. Okay. Okay. Anyway, the Zen Mondo comes until F. Okay. Let me start. So if space-time is null geodesically complete, contradiction happens, something like this. So each gamma has conjugation point, so which makes a compact null segment, And the summation of compact segment is becomes a 3D compact null surface, B3, that surrounds I plus J. So future of time-like geodesics is surrounded by null geodesics. So this is 4 dimension. So the surface corresponds to 3 dimension. And this is no. So by the way, from requirement 1, sigma 3 has time-like vector field. And each point on B3 has an intersection with vector field, time-like vector field. This is null surface, so that's why only one interaction is accepted, maximally, 1 or 0. So each point on B3 cannot be corrected by time-like geodesics. So intersection number is 1 or 0. So makes a smooth injection map of B3 on sigma 3. So the image of B3 on sigma by T is compact because B3 is compact. However, it is well known that a smooth injection of a compact hypersurface without boundary on a non-compact hypersurface with same dimension is in a compact way is impossible. So this is a well-known fact. So this is clearly contradict with each other. That's why null geodesically complete assumption is ruled out. The point is, so if three conditions are satisfied, photon's future cannot be predicted at some point. Okay, so the picture from A to E is shown something like this. So here, sigma 3, and photon B3 is something like this, and which makes a compact, and which surrounds F4 future of time-like vectors. And you can, so from the assumption, there is one-to-one interaction between the global time-like vector and this B3 object, which makes a map in a compact way. However, such compact mapping is impossible. This is what F is saying. So this is impossible picture from A and E. This is the result. So rather, the true picture is something like this. When a star exists, so there is a Cauchy surface. The global time-like vector can be defined. And the star is on a 3D surface. And when it shrinks and makes a black hole, outside global time-like vector exists. However, global time-like vector cannot be defined inside the horizon. So all time-like vector and the null vector goes to one at some point, and it is terminated. In that sense, null geodesically and time-like geodesically, this object is incomplete. Termination does not mean that the photon stops. But rather, we should consider that we cannot calculate what would happen to the photons when they arrive at the singularity, chi. So in that sense, chi is outside of space-time. We cannot calculate anything once photons are absorbed by chi. In that sense, once black hole is formed, the space-time cannot have a Cauchy surface. Okay, this is what we want to say. Space-time is terminated at chi. This is singularity. And this is not just a termination of photon motion, but also space-time itself is terminated. In that sense, general relativity has a limitation. And about 5 years later, Hawking and Penrose showed that a similar situation happens even for Big Bang situation. So if we assume some natural condition at the beginning of the universe, if we believe general relativity, so singular point has to appear. This is a limitation of general relativity. And this is a story about 60 years ago. And after that, many people try to understand more about singularities and the extension of general relativity. And we don't know, so the clear improvement, or there is a clear improvement or not. So this is still uncertain situation. And in that sense, maybe a singularity theorem may be a singularity of human intelligence. And whether the singularity theorem is really a singularity of human intelligence or not depends on current and the future scientists. Thank you very much.
Thank you very much. Thank you very much, Nagataki-san, for great and exemplary 15 minutes talk for the subject of very intricate and aesthetic and very, the description was very pedagogical. Thank you very much. So questions?
So how this third condition process is it? What does it?
Yeah. Thank you very much. So this means this. So Einstein equation comes into the game only this point. So other than that, the theorem is a matter of mathematics and the differential geometry issue. The Einstein equation comes only this part. And this requirement corresponds to this requirement in T million. And for example, for simple perfect fluid, this condition corresponds to flow plus 3 pressure is positive. This is quite natural. So
we have a sort of the dark energy type of equation stage. And then
yes, thank you very much. So you can add the dark energy matter term here. So as long as this is positive, so even if you will include the dark energy part, the Penrose requirement is that this is positive. And normally, for the case of star, dark energy density is quite smaller, so it is visible. So if you like, you can include. Anyway, the requirement is something like this. This is quite a natural requirement, and which is called as a strong energy condition.
Any other question?
So continue the same question. So dark energy in a Big Bang is negligible or non-negligible?
If you would adopt the current dark energy density, it is negligible. But if you go to the early universe, so maybe gamma can have a big value. So the requirement is that this term is positive. So Roger Penrose requires just like this. So if this condition is satisfied, so this conclusion, Singularity Theorem, is solid and unchanged. Did I answer your question?
This is very nice question, but if you consider a quantum effect, then can it save the singularity?
Yes. Thank you. Thank you very much for the important question. This theorem depends on general relativity. So if we believe general relativity, singularity appears. So if you include quantum effects, maybe something different picture is derived. So that's what many people are trying to do self-consistently. I hope this will succeed to understand the inner structure of black hole better than general relativity. Yes.
May I ask, is the connection completeness and privilege of singularity?
Good. Yeah, thank you very much. And there is a almost one-to-one correspondence. So if space-time is incomplete or null geodesics, so curvature becomes infinity. However, some scientists already showed that the exceptional situation. So there is, strictly speaking, there is no one-to-one correspondence. So to be here, singularity is defined as an incompleteness of null geodesics, which is almost corresponding to the divergence of curvature of space-time, but not one-to-one correspondence. Yes.
Yeah. So my next question is, so what's the situation for higher dimensional space? And then my second question is, if time access is not real, it's imaginary. So what will happen?
Yes, good. So if you would accept that the space-time has a Cauchy surface, which means that which must have the global time vector field. This is the almost definition of Cauchy surface. So in that sense, so if you accept Cauchy surface picture, that is global time vector. And for the first question for higher dimension, so you can apply this theory to even for higher dimension. So in that sense, you can go to higher situation case, but the same truth is adopted.
Okay, so Namba-san has a question through Zoom.
Yes, sorry, from Zoom. Well, thank you very much for very nice talk about the singularity theorem. Well, in your opinion, does inflation solve the like initial singularity problem? I mean, during inflation, the strong energy condition is not satisfied. But it is not. Oh, it's not immediate that if the analgesic is complete or not. What do you think?
For the inflation situation, almost these terms are negligible and just gamma determines the energy momentum component. And if I remember correctly, gamma is positive for inflation. Do you agree, Numbers?
Sorry, what is gamma? I guess I cannot see what's written.
Yeah. Sorry. Okay.
So P is minus rho, right? During inflation.
Yes. Yes. P, I don't know, rho plus P plus gamma. Lambda. And this is a requirement of.
Oh, I see. So it's not okay.
And for the inflation case, yeah, something like this. But okay, good. Okay, so yeah, for the inflation case, the situation is something like this. So for the singularity, for the Big Bang, when I am saying Big Bang, which happens before the inflation, after the creation of the universe. So I am saying that Big Bang as a creation of the universe. And once the universe is created, after that, inflation happens. But I am Hawking is saying that the singularity appears before the inflation. If you apply the expanding universe picture, at the initial situation, singularity has to appear.
I see. Okay, thank you.
They disappear?
Yes.
You appear and disappear later, or it's still there?
Appear means singularity appears and disappears.
Still here now, or you mean there's a singularity?
Singularity. Good question. And so yeah, actually, I don't know. Maybe it's corresponding to a white ball, but so this is a kind of limitation of general relativity. And if you believe general relativity, singularity has to appear at the very beginning of the universe. But how it will evolve with time, which nobody knows. So we cannot calculate because it's outside of space-time. This object is outside of space-time. So if it is inside of space-time, everything is calculated by using manifold structure and metric. But singularity is outside. So we cannot calculate what will happen for the singularity and the object which is which has encountered to the singularity. So this is a really future issue. So we have to overcome the singularity problem to understand the creation of the universe or any inner part of the black hole. I believe there should be many questions.
Okay, yeah, I think so. So maybe let's thank Nagataki-san again for the great talk and leave it to the further discussion at his presence. Thank you very much.